Okay, so lesson 9.2 today is on the Pythagorean theorem and its converse. Today's goals are going to be to use the Pythagorean theorem to solve problems involving right triangles and to classify triangles using the converse of the Pythagorean theorem. I think most of you are probably familiar by now with the Pythagorean theorem. It's that equation a squared plus b squared equals c squared. So the full idea is that if you have a right triangle, then the square of the two smaller sides, when you add them, equals the square of the larger sides. So if you have a right triangle, a squared plus b squared will always equal c squared. The converse of that is just saying that in reverse. If you have a shape where a squared plus b squared equals c squared, it must be a right triangle. Okay, so they're not really two separate ideas, they're just looking at it from two different directions. There are many ways that we can prove the Pythagorean theorem. You can look at visual proofs, like you can build a little instrument like this that fills up with water, and you can see that those two smaller squares off the side have the exact same amount of water as the larger square. You can build geometric proofs where you kind of like build kind of puzzle pieces and slide them around. So you can take this and say that, okay, well, my gray empty space here is either going to be written as a squared and b squared, or it's going to be written as c squared, but the empty space never changes. We're just rearranging the pieces, so it gets kind of shuffled around at different spots, but the empty space is always the same. So this would be showing kind of the same idea. Now, in fact, there are not only two there, but if we read over here in this math history minute, the Pythagorean theorem is named for the Greek mathematician Pythagoras, who lived in 570 BC, so that's 2,500 years ago. Although it is believed that Babylonian, Mesopotamian, Indian, and Chinese mathematicians all discovered this theorem independently. So it's named after this guy. That's just because in our country, in European countries, we have a history that goes kind of through the Greeks as the originators of most written ideas, mathematic ideas, cultural ideas. A lot of it comes through the Greek city-states. So we use this name, the Pythagorean theorem, although we can point out that, this is not an invention purely of the Greeks. This is something that's been discovered all throughout the world at different times. To date, there's actually been 370 different proofs of this theorem that have been verified. So 370 different ways to prove that this is true, including one written not so long ago, about 15 years ago, by a 14-year-old in Iran. Now, why do we have 370 different proofs? Why are people so interested in proving this over and over? Why is this such an important subject in geometry? Well, the reason why is because really the Pythagorean theorem describes two-dimensional space, a truth about two-dimensional space, probably better than most any other idea. So if I slow down, kind of go through different dimensions. So if we talk about 0 dimensions, that's a point. So points are just little dots somewhere in space. Okay, a point, a point, a point, just little points floating around in space. There's not much to them. They're just a location, like the location on a graph. It's just a single point somewhere. If you take 2 points, you can connect those, and now you have what we call one-dimensional space. So like, for example, a number line is one-dimensional. It goes just in one direction, kind of horizontally. And we can stick numbers on there. We can say 0, 1, 2, -1, -2. Okay, but these numbers are all representing locations within one dimension of space. Okay, so that's what happens if we connect 2 points. 2 points in space, wherever we put them, if we connect them, we now have one dimension that we're looking at. Well, what happens if we connect 3 points? Well, 3 points, no longer does that just give us some length in one dimension, that gives us some kind of area in 2 dimensions. And when we connect 3 points, we always make a triangle. That's why we've been studying triangles so much, because triangles are like the most basic shape within 2 dimensions. Okay, so anything flat, anything you write on a piece of paper, the most basic version, if you just kind of randomly create a 2-dimensional space by picking 3 points and connecting them, what you've created is a triangle. Now, those triangles are not always right triangles. However, those triangles do always contain right triangles. So there's a way to cut them up so that you always can create 2 right triangles. So basically, the idea is that any 3 points in space we'll create two right triangles that are back to back. Okay, so this is kind of the most simple image of a two-dimensional space that we can talk about. Now we can talk about other things. We can talk about, like hexagons, circles. We can talk about ovals. These are all different types of two-dimensional space. But generally, these things are what we move on to after we understand the simplest, most basic shape, the triangle, first. And we want to understand it as well as we can. Okay, so within that right triangle, we have that idea that a squared plus b squared equals c squared, okay? Which is very different from a plus b equals c, right? We're not saying this. Okay, that is not true. You can kind of make sense of that in this picture if you just imagine, all right, take this length, kind of lay it down right there, take this length, lay it down right here. Well, they're going to overlap here in the middle. They're not going to be the same length. If I kind of like pressed in on this corner so that A and B stretched out to make a straight line, well, C is some distance here, but A and B together, like let's say a different way of saying that, let me take A here and lay it sideways, right? So it's like that instead of going up here, we're going to say A goes out to the right. Well, we can see that A plus B is bigger than C. And it always should be in a triangle. Those two smaller lengths are always going to be larger together than the hypotenuse. However, if we square it, a squared plus b squared equals c squared, if we talk about not the lengths themselves, but the squares off of the side of those lengths in a right triangle, then what we get is we do get something, oops, didn't work out very well. Then what we get is we do get something where there is a relationship we can describe. And that relationship is that these two smaller areas, the b squared and the a squared, those two smaller areas will add up to the larger one. And that's what we're seeing when we're looking at something like this, right? Those two smaller areas add up to the larger one. Okay, so there's an idea called a Pythagorean triple. Now, Pythagorean triple is just a triangle where the lengths of the sides are whole numbers. So for example, 3, 4, 5 is a common Pythagorean triple. So if I have 3, 4, and 5. Well, let's think about what we get when we square those. So 3, let me draw that a little differently, make it a little smaller. 3 squared would be 9. So right, the area there would be 9 when I do 3 times 3. 4 squared, it's going to be 16. And 5 squared is going to be 25. 9 and 16 add up to make 25. So this is a particular right triangle where the numbers are whole numbers. Now, if I wanted to say like one side is 3 and the other side is 5, what is the length of the hypotenuse here? Well, this won't be a Pythagorean triple. So all that means is that this number will not be a whole number. It'll be like, I don't know, 6.2, it could be 5.9. It's going to be something that has a decimal. It's going to be bigger than either of these two, but it's not going to be a whole number. So there's a series of these that kind of work out. And here, kind of the most common ones that don't get to be too big. So 3, 4, 5 works. Now, in the same sense that 3, 4, 5 works, 30, 40, 50 works. 300, 400, 500 works. So any multiple of 3, 4, 5 works. So even if you didn't have to multiply by 10, even if you just doubled it, so 6, 8, 10, that would also work. Let's try that one real quick just to confirm. So if I have 6, 8, and 10, well, 6 squared is 36. 8 squared is 64. And 10 squared is 100. Okay, well, 64 and 36 add up to 100, so that looks good. So they're saying 3x, 4x, 5x. This just means multiples of 3, multiples of 4, and multiples of 5. So I could choose any value for x. So I could choose, 7, and I could say 3 times 7, 4 times 7, 5 times 7. Those would be a Pythagorean triple, as long as you have that 3, 4, 5 ratio. It also works if you have 5, 12, 13. So 5, 12, and 13 work. 8, 15, 17 works. 7, 24, and 25 work. These are just common Pythagorean triples. These ones I don't have memorized. They are common ones, and it wouldn't hurt for me to kind of have these committed to memory a little better. This is the one that you really should know, that 3, 4, 5, and every multiple of 3, 4, 5 is a Pythagorean triple. Okay, so in example 1, in our next video, we'll go through and practice using the Pythagorean theorem to interact with some drawings, try to solve for missing lengths on the sides of a right triangle.